Hi everyone, welcome to lecture 9, proof system stack, recursion, and composition. So this is a really long name and it seems like an arbitrary collection of seemingly unrelated concepts, but it isn't. And I promise you by the end of the lecture, you'll see how the modular modern proof system stack actually leads to easier recursion and proof composition, and as well as why recursion and composition are interesting and useful. So how we're going to progress today is in 4 parts. First of all, we'll do an overview and a taxonomy to situate you in this series of lectures so far. And then secondly, we're going to basically go through 2 end-to-end constructions of the proof system stack. So the first is sort of the first generation non-modular and non-universal model. This is used by Groth 16, for example. This is used by Pinocchio. And this is not used so often anymore. And that's because it's not universal and requires a circuit-specific setup each time you want to write a new application. So we're going to, from there, progress to the modern proof system stack, which is a significant part of it is based on something called the Planckish IOP and Planckish arithmetization. So we'll see here with the introduction of the information theoretic model known as the algebraic holographic proof or the polynomial interactive oracle proof, and we'll explain these terms. But with the introduction of this very flexible information theoretic model, we actually get a modular construction, and having a modular construction allows us to basically swap out backends and to optimize the proof system across the stack. And then lastly, we're going to see how proof systems based on AHP and PIOP actually give us efficient full recursion. So the intuition here is that these pre-processing SNARKs move a lot of the encoding of the circuit to a pre-processing stage, so outside the verifier. And in recursive SNARKs, we want the verifier circuit is precisely what we're trying to embed at each recursive step. So we're going to see how modular proof systems give us better recursion. And we're also going to see certain strategies for recursion that don't require sublinear verifiers. And lastly, if we have time, we'll talk about proof composition. And proof composition differs from recursion in that it is the composition of different proof systems, whereas recursion is just recursing instances of proofs within the same proof system. So we're going to start off with an overview, and I'm going to draw my favorite diagram, which is all the components of a modern SNARK. I hope you're tired of this diagram by now. So we start here with some way to check the correctness of an arbitrary computation. So this can be a very complex and very large computation. We apply arithmetization in order to reduce this check to an efficient circuit satisfaction check. So this check can be done probabilistically. So for example, a probabilistic check of a single polynomial identity. Now, the arithmetization that we choose limits the choice of information theoretic models that we can use to check this circuit satisfaction problem. So the modern SNARKs use something called the interactive oracle proof for the information theoretic model. And now this model makes lots of idealized assumptions, and it is secure against computationally unbounded adversaries, provers and verifiers. But in order to instantiate it in the real world, we need something called a cryptographic compiler that introduces cryptographic assumptions. But it also introduces very desirable properties like efficiency, like enforcing point queries, enforcing the desired behavior of the prover. And with the crypto compiler, we finally get out our argument system. So last lecture, Jason covered an end-to-end proof system called Plonk. And we're just going to, as an exercise, fill in the different components of Plonk over here. So for arithmetization, Plonk represents, Plonk encodes the values of its assignments as univariate polynomials in the Lagrange basis. And it basically does this. It basically conceives of this circuit as a series of gates. And we saw the Plonk gate being made up of addition and multiplication. But we also heard some hints that it could be extended to support custom gates that are even higher degree. Now, from these polynomials, to check the correctness of these polynomials, Plonk uses a polynomial IOP. And to instantiate this polynomial IOP, it uses a polynomial commitment scheme called KZG commitment. And you get Plonk. So now, the first example we're going to do today is actually not Plonk. It's actually, like I said, from the first generation of proof systems. So it's called Pinocchio. Basically, Groth 16 is an optimized version of Pinocchio. By optimized, I mean that it does some fancy tricks and it reduces the size of the proof, but it increases like computation. So, but Groth 16 has it has the smallest proof size known, and something is the smallest proof size that's theoretically possible. So these are very much in the same family of proof system. So how these proof systems look is they start off, we were writing something like zkSNARK, right? So maybe there's a high-level language that you specify your business logic in. We convert that to an R1CS rank 1 constraint system. And we're going to go through this later in more detail. But this was from lecture 7. And converts the rank 1 constraint system to a quadratic arithmetic program. And how it checks this quadratic arithmetic program is using something called a linear PCP. Or a linear IP. So PCP is probabilistically checkable proof. It's a mouthful. And IP is interactive proof. So linear IP is just a multi-round linear PCP. But the point, you will see later on that basically, and for the crypto compiler, it uses pairing-based cryptography. So you'll see later on that these two components, the information theoretical component and the cryptographic compiler, are very intimately linked in Pinocchio and Groth 16. In fact, they're not possible to separate. This is what makes Pinocchio and Groth 16 different from the modular modern SNARKs. And later on, in fact, we'll see that some proof systems sort of cut it off here, right? Or even here. They cut it off at the R1CS. And they use some other way to convert the R1CS to a series of low-degree polynomials. And from there, they then instantiate a polynomial IOP to check it. So examples of proof systems that do this are Marlin and I think something called fractal. There was another one, I'm kind of blanking, but it's in the lecture notes. Yes?
So wait, typically these are different schemes that also use R1CS, or that they don't use R1CS?
So Marlin and fractal, the question was, do they use R1CS? Yes, they do. Marlin and fractal use the R1CS arithmetization, but they don't want this junk here. They don't want this non-modular sort of pairing-based IOP and crypto compiler. So instead, they sort of massage the R1CS from matrix form into low-degree extensions, into polynomial form. And then they do some clever tricks to allow the verifier to cheaply access and query these polynomials using a polynomial IOP. And because they do that, they achieve modularity at this step. So, for example, Marlin, when you reach the PI polynomial IOP step, you can have your choice of cryptographic compilers. You can choose KZG, you can choose Fry, you can choose the inner product argument. And so this really helps R1CS fit in with the rest of the modern modular SNARK ecosystem. Cool. So what we're going to do now is go through an end-to-end example of the proof system Pinocchio. And this is similar to Groth16. Groth16 is an optimized version of Pinocchio. So let me write out the whole stack again. So we go from R1CS to QAP. To check the QAP, we use linear PCP. And then to instantiate the linear PCP, we use pairing-based cryptography. This is the stack used by Pinocchio. So we're going to break this down into 3 steps. And, well, also you might ask me why I'm bothering to show you an older proof system. My objective here is to impress upon you the importance of modularity and also to show you exactly where these proof systems stop becoming modular. Yeah, I find it pretty interesting, but even for historical purposes. So what I'm writing out right now is the linear PCP that Pinocchio uses to check the QAP. And as I said just now, the linear PCP is inextricable from the pairing. Yeah. So this check proceeds in 3 steps. The first is a divisibility check. And we'll see what this means later. And the second is a linear combination check. And the last is something called the coefficients consistency check. So all this will make more sense when we remind ourselves what the QAP actually is. So from lecture 7, we remember like the R1CS to QAP transformation. So what we're going to do is we're going to start out with an arithmetic circuit here. We're going to convert it to R1CS, which is 3 coefficient matrices, the left, right, and center matrices, representing the left, right, and output wires to the gates in the circuit. And then from the matrices, we're going to get, finally, our QAP, which contains the same information, which checks the correctness of the matrices using a single polynomial identity, a probabilistic check of a single polynomial identity. So very quickly, we can represent a program as a bunch of wires and gates, addition and multiplication gates. And these gates correspond directly to something called like the flattened constraints form. So where we have a left variable, we have a right variable, and we have an output variable. And one quirk was that addition, there's unlimited fan-in addition in R1CS. So terms that are added, they all get squished into the into the left variable. Now, the next step to get to R1CS, we basically collect all the coefficients of the left, right, and output wires, and we put them into these big matrices. So let's say for the output matrix, and by the way, over here I'm going to number the gates G0, G1, all the way to GD. I have D gates. And I'm going to label the wires W1, W2, all the way to WM. So I have M wires. So to collect the coefficients for M wires and D gates, the M wires of D gates, I'm going to make an output matrix that it has D rows and M columns. So in the columns, we index the variables, the wires. And on the rows, we index the gates. And so these are the coefficients of each variable at the output wire of each gate. So another way of saying this is that O, I, J is the coefficient of the output wire of gate I. The coefficient of is the coefficient of the jth variable at the output wire of gate I. Yeah. I don't have a succinct way to write that down, but that's what it is. And similarly, we construct these for L and R. And at the end of the R1CS representation, we basically have an equation that's made up of three linear operations. So for a satisfying witness A, we should get that LA times RA minus OA is 0. the 0 vector. All this should be just a recap. And our last step to convert from these matrices into a polynomial identity, we basically end up with a polynomial identity Lx times Rx minus Ox that should evaluate to 0 on all I in D. So on all gates, this polynomial identity should evaluate to 0. And by the way, the satisfying witness information is hidden inside these Lx, Rx, Ox. And this is sort of your first intuition into why this is an LIP. So it's a linear interactive protocol, an LIP. So how we construct Lx, for example. We construct Lx as a linear combination of what we call the LIX polynomials. What is LIX? Sorry, let me call it LJX to be very consistent. What is LJX? LJX is the Lagrange interpolation polynomial of the jth column of the L matrix. So maybe let me change this to O. Right, so this is O0x. This is O1x. And what we're doing is we're taking each element of our witness and using it as a coefficient for the corresponding column in our matrix. And the linear combination of this we call OX. So if we do the same thing for LX and RX, then we expect that this polynomial identity holds. And if this polynomial identity holds, then its quotient, when divided by Tx, the vanishing polynomial over the evaluation domain X, its quotient should be some polynomial. So the evaluation domain here, like we said, is simply 1, 2, 3, 4, all the way to D. It's all the gates in indices. Okay. No surprises here. So now that we have our QAP, let's construct this LPCP to check it. Any questions? Okay. So the first check that we're going to do is precisely this check, the divisibility check. And sort of the next two checks fall out of this first check being inadequate. It falls out of having to prevent prover cheating strategies. So now to check this identity, what we have to do is we basically have to force the prover to take linear combinations of the allowed polynomials. So these LIs, so our QAP is defined by the LJs, RJs, and OJs. And this is public information. These represent the information encoded in the coefficient matrices. So our QAP is defined by these public polynomials. And these contain no information about any satisfying witness, right? Well, and there's also Tx over here. Also a public thing. Everyone knows the evaluation domain. Everyone can compute Tx. So now given this QAP, what we're going to do is we're going to introduce a secret element into it. We're going to introduce a secret evaluation point S, sampled randomly. And as some of you might be familiar with this, in real life, we get this secret using a multi-party computation. And someone's implementing this, in fact, in Swift this weekend. So we sample some secret evaluation point S. And we basically compute the evaluations of these public polynomials at the secret point S. So we compute the LJSs. We compute RJSs, and we compute the OJSs. Oh, I forgot to write over here. So yes, this is essential notation. These square brackets with a subscript 1. This means that we are outputting a commitment to the evaluation of these public polynomials at S. And that's different from outputting. That basically means we don't output any information about S. So I just want to quickly remind you about why this works. These last two lines here, let's look at these. So if we want to evaluate some public polynomial, P, on a secret evaluation point S, what we can do is we can pre-compute commitments to the powers of S. So S0 sub 1, S1 sub 1, S2 sub 1. And the important thing here is that given, for example, S sub 1, and I'm using this notation here to mean S times G, a scalar multiplication. So given S sub 1 and given G, in fact, you still don't know S. And this is called the discrete log problem, and it's hard in the group that we've chosen. Okay? So in our trusted setup, we got a secret point S, and we evaluated all our public polynomials at the secret point S. And we got out a series of commitments to these evaluations. And at the end of the day, we're none the wiser about what S might be. And yet, we've still, in a way, managed to evaluate our polynomials at a secret point. So we might not get out LJS, but we do get out the commitments to LJS. And we do the same as well for T, our vanishing polynomial. And we call this tuple our so-called SRS, structured reference string. The structure refers to the fact that it's using a very structured increasing powers of the same secret point S. Later on, we'll see that for the KZG commitment, for example, the setup is a universal setup because it just produces random generators with no structure. But because this setup required some structure, oh, sorry, did I say KZG commitment? I meant to say vector Patterson commitment. So for the KZG commitment, absolutely, it's a trusted setup. For the vector Patterson commitment, it's a universal random setup. And over here, it's absolutely a trusted setup as well. Any questions? It's so quiet today. I either am explaining it super well or everyone's lost.
Is this like KCG? Is this like a special?
So the question is this like KZG? I suppose it's similar in this setup phase where we're computing evaluations on a secret point. But first of all, this is a different kind of object. So this is not a polynomial commitment scheme. this is a way to check some polynomial identity. And this is kind of a bespoke linear PCP constructed just to check the correctness of a QAP. But you might see some similar tricks. And in fact, we're going to use a pairing check. The verifier is going to use a pairing check at the end of it. Yeah, but these are different objects. Yeah. So now using this SRS, what the prover can do is the prover can actually compute a commitment to the evaluation of L at S. So if you recall, L is a linear combination of the LJs. Well, here I've written O. So L is a linear combination of the LJs using the purportedly satisfying witness as the coefficients. So basically here, the prover can commit some kind of commitment to their secret witness evaluated at the secret point S. So how they would do this is they would simply use the information from the SRS. So they have the commitments to the LJSs. And of course, they themselves know AJ. And just as a reminder, J indexes the number of wires. So once again, the prover can produce some kind of commitment that contains the information of their satisfying witness, and at the same time uses, it creates linear combinations using the allowed and the public R1CS QAP polynomials evaluated at some secret point S. And why this step is important is because the prover does not know S. So the prover has no choice but to take linear combinations of the commitments to these polynomials evaluated at S. Yes?
It's not a commitment to A values, right? It's just the A values directly. You have brackets in it, I'm not sure.
Oh, yeah. So, yeah, my notation is, it gets kind of hairy here. Let me just remove this bracket here and put times G1.
Oh, or like, why are there brackets around the A values?
Oh, why are there brackets around the A values? Right. Thank you for that question. So, I think, let me write here, like, this is the notation I'm going to use. It's additive notation. So, when I write something like this, alpha is in the scalar field, and G is in the group whose, so what alpha is in the scalar field means is that it means it's an element of Fp, where P is the order of the group G. Now, in other words, elements from Fp, they enumerate the elements in G. And so to multiply something in G by something in Fp is a sensible operation. So when I write alpha G, what I mean is G plus G plus G alpha times. Okay? And this is called additive notation. If I wanted to do multiplicative notation, I would write G to the alpha equals G times G times G alpha times. But I choose I choose the correct option. So now okay. Sidebar. So what I mean here, this aj in the brackets, is a scalar multiplication. I'm using aj to multiply this group element that I got from the trusted setup. I do the same thing for my right and output polynomials. And I also do it for actually my quotient polynomial. If you recall, my quotient polynomial is this is what's going to convince you that I have a satisfying assignment for this relation in the numerator. The fact that its quotient, when divided by the vanishing polynomial, actually gives me a valid polynomial h. So this is the proof, by the way. Pi equals this. And so now what the verifier is going to do is it's going to do a pairing check on these commitments to your satisfying witness that you constructed. So I'm just going to write down the pairing check, and let's try and figure out why it works. So the pairing check is firstly a pairing between your commitments to your left and right polynomials minus pi o, the output. And in this second element of the pairing, we're just going to put in the identity. The generator G1. Oh, yeah. So the question is this a self-pairing? Yes. I am going to, for today, I'm going to use a symmetric pairing. It takes two elements from the same group G1 and maps it to a third element in the target group GT. And if we wanted to write it for asymmetric pairings, we could, but this simplifies my life a little bit. Sorry? Why don't we always just use this? That's a good question. I'm not sure. I would guess that this would just limit our choice of elliptic curves. The standard constructions for pairings are asymmetric. If I wanted to make my proofs work for asymmetric pairings, I would just move some things into group 2. So I could. I just don't want to. Now, so on the left-hand side of the pairing check, we have this. This should look suspiciously familiar. And on the right-hand side, we're checking the pi h that you gave us for your supposed quotient polynomial. And we're using the commitment to the evaluation of the vanishing polynomial. We got this from our trusted setup over here. This is a publicly known group element. So let's see why this works. Basically, this pairing check is equivalent to doing the following check in the exponent. It's equivalent to checking that LS in the exponent times RS minus OS equals HS times TS. And basically, this tells me that you have a satisfying assignment and that HS is actually a polynomial.
Can you tell your
Oh, yeah. Thank you. So it's a pairing check. We have 3 pairings, actually. Here. How am I doing on time? I can't. I have 45 minutes left. Okay. So, given that information, what I'm gonna do is I'm gonna just go through these 2 additional checks without deriving them in full. They are derived in the lecture notes. So like I said previously, these checks kind of fall out of the inadequacy of the first check. So now if we just had the first check, so what are we getting from the prover? We're getting 1, 2, 3, 4 group elements. And we ourselves have a commitment to the evaluation of the vanishing polynomial at S. So why can't the prover just send you like 4 group elements that have nothing to do with the L's, R's, and O's from the trusted setup? So 4 group elements that maybe encode some other circuit for which their witness is satisfying, but has nothing to do with your circuit. Yeah, you have no way of knowing. And really what you need to do is you need to check that these pi L's, pi R's, and pi O's were constructed from the L's, R's, and O's that you provided in the SRS.
Pick S or the verifier?
So the question is, does the prover pick S or the verifier? So the answer is neither. S is picked before, it is picked in the setup phase, before the protocol even starts. I suppose it'd be okay if the verifier picked S though. But then that allows the verifier to make fake proofs, if you care about that. So in real life, S is picked, or the powers of S are computed using a multi-party computation such that no one party knows S, and everyone would have to collude in order to recover S. So we absolutely should not know S. And if we did know S, we can make fake proofs. There's a homework question related to that from lecture 5, I believe.
So S would have been picked as part of like a KCG ceremony?
Yeah. We would compute the powers of S using some kind of MPC. Exactly. So in order to check that the pi L's, R's, and O's were in fact constructed from linear combinations of the SRS elements, what we do is we introduce a shift. What I mean by this is we introduce some alpha shift to each of those Li's, Ri's, and Oi's. So we compute in the setup. Again, this alpha has to be secret. So we compute in the setup now alpha prime j's at S, commitments to some kind of shifted LJs at S. And how we shifted them is we just introduced an alpha shift. So a coefficient of alpha. Alpha L. And so prover doesn't know alpha and doesn't know S. The only way the prover could produce another pair that also has an alpha shift is if one pair is a linear combination of the other. So what I mean by this, so the prover, now in the trusted setup, we introduce these L prime JS's. So correspondingly, the prover uses them to construct pi prime L. And it's basically the same thing as pi L, but using these now shifted commitments that you've provided in the setup.
Do we use the same coefficients or do we use different?
The question is, do we use the same coefficients to compute pi prime L's? Yes, we use the same coefficients. So let me write it out, and hopefully it'll become clear what we're trying to achieve. So we again use our satisfying assignment as the coefficients, this time to the L prime J's, the commitments of the L prime J's evaluated at S. And what is left for the verifier to check is basically that this alpha shift holds between the original pi L and the new pi L prime. And since the prover did not know L, the only way they could have computed this exact shift was if they made use of the LJs and the shifted LJs. That's the only place that contains any information about alpha. Now, any questions?
The verifier also doesn't know alpha, right?
So the question is, does the verifier know alpha? And the answer is no. It's a secret, just like S. I guess if the verifier knew alpha, I guess once again the verifier could use that to make a fake proof. Yeah, that doesn't actually make use of the LJs and RJs from the SRS.
How do they verify the relationship then? If they've got sort of this pi L and pi prime L, and the
Yes.
difference is this alpha coefficient is really the scalar, if they don't know, how do they actually verify that the two are?
Yeah, so the question is, since the verifier doesn't know alpha, how are they supposed to verify some factor of alpha between pi L and pi L prime? Right. So it is true that the verifier doesn't know alpha, but what the verifier does know, and I'm realizing now that I forgot to write it here, which is why I think you're confused. The verifier knows the commitment to alpha over here. Right. And so you can see what's going to happen. This commitment to alpha is going to go into the pairing, and it's going to get checked in the exponent. So we're checking this alpha shift in the exponent. Yes?
So all these alphas are generated in the second trusted setup?
Oh, okay. So the question is, are these alphas generated in the second trusted setup? And my answer is that there's no second trusted setup. I split up this check into 3 parts to make it easier for all of us. If you go and read the paper, it's presented as one huge check. And it's hard to figure out like why. It's hard to figure out why certain things are being introduced and what the elements of the SRS are doing. So this is a kind of reverse engineer for exposition.
But then, like, who generates the alpha?
Who generates the alpha is the same people who made the S, the powers of S.
Oh.
Yeah.
So there's like one. Oh.
This is one thing. I split it up into 3 for us to digest.
But isn't the alpha is like circuits
So the question is, isn't the alpha circuit specific?
Oh, you just also compute alpha times S or something.
Yeah, so first of all, let me point out something. Is the moment we started, our very first SRS that I presented was already circuit specific.
Yeah.
Yeah. The alphas, are they circuit specific? I guess not. I guess if you computed a random alpha previously, you could reuse it. Or could you? Well, sorry, there was a question there.
Sorry, why is
And
the
use it.
first part of the setup circuit specific? Because if you just have powers of,
So the question is, why is the first part of the SRS circuit specific? The first part meaning the commitments to the evaluations of LJ, RJ, and OJ at a secret point S. Now, what is your circuit? Your circuit is precisely, oh, I forgot where I wrote it, but yeah. So your circuit, your QAP, is defined precisely by the LJs, RJs, and OJs, the coefficient matrices that define your circuit.
Yeah.
Yeah, and it's gonna be different for a different circuit.
but if you have all the powers of that,
Oh,
then can't I, like, with L on or
so the question is, if I have all the powers of S, then can I just reuse them? Yes, you could, which is why actually you don't have all the powers of S. That's not part of your SRS.
Oh.
I didn't write that anywhere. Yeah, you have the evaluations at S of your circuit-specific polynomials. In fact, you have the commitments to those evaluations. Yeah, but you do not have like S. That's not provided.
that if you have those?
Would it be bad if we had those? Let's see. Would it be bad if we had those?
I guess I'm just trying to understand. This is like whether you are happy to take it offline.
Yeah.
But, like sometimes the MQ split into phase 1 and phase 2.
Yeah.
Compute a bunch of powers. I'm wondering if that's
Yeah. Oh, okay. So the question was like, sometimes the MPC is split up into phase 1 and 2. And in phase 1, we compute just the powers of some secret point. Yeah, I actually don't know if that's the same secret point as this one.
not super relevant to
Okay, let's figure it out. I'll ping you everyone in the Discord. I actually don't know.
Because yeah, the graph you're seeing paper, like the second part of the setup looks a lot like this, basically. So it might just be like some.
But is it the same secret that they use?
I think so.
It is? Okay.
It doesn't matter.
I don't know. Cool. So I have now 30 minutes left. That's officially not enough time. So what I'm gonna do is I'm just gonna hand wave the last part. So so the coefficients consistency check, what it is. It's looking at your pi L's, pi R, and pi O. And it's asking how do I know that you use the same AJs to compute each of them? Maybe you did like BJ, RJ, so on. So that's actually not constrained by the previous two checks. And so to check that, we introduce basically a shift of the combination of your pi L, pi R's, and pi R's. So it's gonna look something like this, like a beta shift of this whole thing. So the intuition is that you're checking some shift of this whole thing. And if you're able to produce that shift, then you must have used the same coefficients. You must be able to basically factor out the coefficients. Okay. So what we've done so far is we've gone through, this is Pinocchio. And I've actually presented Pinocchio without zero-knowledgeness. This is just Pinocchio used for succinctness. And basically, you can see that the circuit-specific information is encoded in your SRS. And you can also see that all the verifier checks are done in the coefficients. They're done as part of pairing checks. And it's very, very hard to separate out the way you've chosen to check this using your linear PCP, linear queries. It's hard to check this any other way besides with pairings. So as I was mentioning just now, wow, I really am blanking on the other proof system. There's Marlin, Fractal, Spartan. Did someone say that? It just came to me anyway. Okay, so these are examples of proof systems that they basically cut off the stack here at R1CS. They said QAP, no thank you. Linear PCB, nope. Pairing, nope. And what they did was they converted the R1CS, the matrices, into a polynomial forms. And they constructed some clever protocols usually involving some kind of sum check protocol to allow the verifier to efficiently make queries, make point queries to those polynomials. And so actually, Marlin in particular is very, very similar to a proof system that you're familiar with, Planck. So both of them on the back end, they both use a polynomial IOP and polynomial commitment scheme. So there's Marlin KZG, for example. They both encode assignments as polynomials in a Lagrange basis over some multiplicative subgroup as the evaluation domain, so over the roots of unity, for example. Where they differ, where Planck differs from Marlin, is in the arithmetization. So Marlin uses R1CS. Planck uses something called RAP, which means randomized error with preprocessing, where error means algebraic intermediate representation. So anyways, Planck uses an arithmetization that doesn't limit itself to degree 2 gates. With Planck, each gate can be an arbitrary number of multiplications and additions. And the reason why Planck wanted to move into this domain is because they no longer have this restriction of the quadratic degree 2 gate that was imposed upon Pinocchio, for example, by pairings. So pairings are a bilinear map. And we don't have k-linear maps that are higher than 2. So the quadratic arithmetic program represents really the theoretical limit of how general your arithmetization can be if you're checking it using a pairing. Now in Planck, we're no longer using some kind of information theoretic model that is entangled with pairings. Then the verifier checks can be performed in the clear instead of in the exponent. So if you look through the Planck paper, we're multiplying like evaluations of the polynomials, commitments of the polynomials in the clear. not in the exponent. I just want to preempt, some people might ask, like, isn't there still a pairing check at the end of Planck because Planck uses KZG? So yes, that pairing check is different from this pairing check. That pairing check is for the commitment scheme. If I swapped out a commitment scheme, for example, I wouldn't have to do that pairing check. And that pairing check is for the evaluation of a polynomial. It's not directly checking the identities. It's not directly doing the verifier's work in the IOP. Cool.
Can you say that again? Why is it different here? Over here you're using the pairing check to check for all each.
Oh yeah. So the question is how are pairings used in Planck versus in, for example, Pinocchio? So in Planck actually doesn't even need a pairing check. If we swap out a polynomial commitment scheme, for example, if we used, let's say phi is just a bunch of Merkle hashes, right? It would do the job equally well. Now, the Planck paper happens to use the KZG polynomial commitment scheme, which has a pairing check at the end. That pairing check is used to evaluate, to verify an evaluation claim about the polynomial. In this case, it's the quotient polynomial, right? Whereas over here, the pairing checks that we did are basically directly checking the polynomial identities specified in the LPCP. Yeah, so they are not separable from the LPCP. Whereas in Planck, they're absolutely separable from the IOP.
Okay, thanks.
Yeah. So with what time I have left, I'm going to switch to to my slides. Yeah, this is a multimedia experience.
Wait, I'll do it.
Okay. So, yeah, with what time we have, we're actually going to explore why this modular stack and why modern SNARKs make it easier for us to do recursion and proof composition. And also why that's a good thing. So, okay, gonna put on my glasses. So this is the punchline of this last section of the talk about recursion and proof composition. So how recursion differs from proof composition is that recursion is basically, recursion is composition within one proof system. And it's often used to reduce the prover's computational complexity and to break down a huge circuit into manageable iterative steps. Now, proof composition takes this one step further by allowing us to embed subprotocols that are from different proof systems. So for example, we could verify a Planck proof in Groth16, for example. That's proof composition. And my claim is that recursion plus proof composition equals fire. So I'm just gonna, oh yeah, I think it's worth going through a few applications to convince you of why you should care. The first, maybe most well-known application is a succinct blockchain. So right now, a blockchain-like client is too resource strapped to replay all the history of transaction execution by itself. So what it does is it simply trusts the full node. It downloads the current state from the full node and trusts that it's correct, which is dangerous because the full node could be lying. Now, what would be better is if the light client also got some kind of proof that the last state transition was correct. So at least it knows that you got there via one valid state transition. And what would be nice is if we had a proof for each state transition in this whole chain of history. But that would quickly become unwieldy, and that would really, the light client would have to check a lot of stuff, a lot of proofs. Remember, your light client is resource constrained. So what if we had a proof that could, at the same time, convince you of the validity of one state transition, as well as the correctness of a previous instance of a state transition proof? So it convinces you both that the most recent state transition is correct and that the history of state transitions up to that point has been correct. So this is what a recursive proof can achieve. And what the light client does is just downloads the latest recursive proof. And that should be enough of a guarantee. So any questions? This is the most obvious application. There's a bunch more that are really cool. So for example, verifiable delay functions. For example, if you have some kind of architecture that is large but structured and repeating, then you could try and attack it and break it down basically into iterative steps. It's the same idea. And for example, really what I've presented so far is the same state transition function being verified over and over, but with recursive proofs, you could go even further, and you could construct not just a linked list, but any directed acyclic graph, and not just of homogeneous proofs, but proofs of heterogeneous statements. So over here, it's like TinyGrat, which is a ML library, and it breaks down into these opcodes that are then composed in this tree. So this would be a cool way to do a large machine learning model using a directed acyclic graph of recursive proofs. So I hope that you now care about recursion and proof composition. Now, why modular proof systems make it easier to do recursion and proof composition? The first reason is because these modern modular proof systems use something called the algebraic holographic proof. And algebraic here just means polynomial, basically. Now, holographic is a really fancy word. Holographic basically means pre-processing. So a holographic proof moves a bunch of information. It encodes a bunch of information about the circuit in some pre-processing phase. And so the verifier no longer is tasked with the burden of reading the circuit in full. Instead, the verifier has oracle access to the encoding of the circuit using, for example, the encryption of the queries in the structured reference string that we saw in Pinocchio. So the effect of this is that you get a smaller verifier. And with a smaller verifier, you can achieve full recursion with better concrete performance. So this is how full recursion works. It's pretty mind-bending, but not compared to the later schemes that I'll show you. So let's try and understand full recursion. So yeah, a normal zkSNARK is just some circuit f. You prove that f of zi wi gives you the output zi plus 1. And you have a proof that this was a correct transition. Now, a recursive proof is basically this application circuit bundled with some verification circuit. And the input to this verification circuit is, in fact, the proof of the recursive circuit. So the proof of these two circuits as a bundle is input into the next verifier, for example. So now the proof then of this circuit would convince you of the correctness both of f as well as of this pi, right? And this pi was proving the correctness of the previous f and the previous pi, and so on. Yes. So the insight here is that you can write anything you want in a circuit. And in fact, you can write a verifier for another circuit. Yes. Cool. So you can see why having a small verifier is good here. If your verifier, for example, were linear time, then at each recursive step, the statement that you're verifying grows, and you get blow up soon enough. So for full recursion, you need a sublinear verifier. And AHP gives you concretely a good sublinear verifier. Yeah. So I'm going to, so here's an example from a library called Plonky 2. It's actually one of the libraries in the Plonkish family. It uses Plonk arithmetization, but not KZG. It uses a Fry-based polynomial commitment scheme. So yeah, Plonky 2 does full recursion. It puts the Fry verifier inside the circuit. Sublinear verifier. And yeah, here's some code I copied from their repo. They're doing a few rounds of recursion to basically shrink down the size of their proof. Why does recursion shrink the size of the proof? Is because the verifier is sublinear in the size of the statement being proven. So each time you're verifying a smaller thing. So now, so that was full recursion. There are actually other ways to achieve recursion-like behavior, even without fully sublinear verifiers. So for example, the inner product argument has a linear size verifier. And yet, we're able to use it to achieve incrementally verifiable computation. And how we do this is we instantiate something called an accumulation scheme. So I won't go through it in detail, but the intuition is that we amortize the expensive check across a batch of proof instances. And at each step, instead of trying to embed the whole linear size verifier, we embed just the accumulation verifier. And the accumulation verifier checks some very cheap log n checks. And it checks, in addition, that you have updated the accumulator properly. The accumulator is where you're basically compressing all that information that you're not checking. So if you're not checking it, it's absolutely essential that you're at least updating it correctly, such that when we reach the end, we can finally perform the linear time check. And if it's been updated correctly this whole time, and it passes the final verification, then we're convinced of the whole history of computation. So, and then there's a further optimization of this called split accumulation that further reduces the recursive threshold. And we don't have to go into this. I will just mention that I know some people here are interested in NOVA. Nova is an example of split accumulation. Yeah. So in split accumulation, the requirements are further relaxed. You don't need a sublinear verifier, first of all, but now you don't even need a sublinear argument. Your argument can be huge. And that's still fine because you're not trying to read the whole argument at each recursive step. So the recursive verifier only reads the public part of the argument and accumulates the rest. Yeah.
Really good question. Wait, is there any specific difference between split accumulation and folding?
So the question is there a difference between split accumulation and a folding scheme? If you read the NOVA paper, they'll say this is a folding scheme. So I think there's no difference. I think there's no difference, yeah.
So this is split accumulation is used with Halo 2 or with Halo 2?
So the question is, can split accumulation be used in Halo 2? Halo 2 currently uses atomic accumulation, which is the previous thing I showed you. Halo 2 does have a succinct argument. It has a log n sized argument. Now, but if you wanted to use split accumulation with Halo 2 and the inner product argument, you could. Basically, at each step, you would just do like the Pedersen commitment. And then at the last step, you could do an inner product argument to shrink the size of your argument. Yeah, so it's the Halo 2 people are actually considering implementing split accumulation. How much time do I have? 8 minutes, okay. That's okay. So these are different ways to achieve recursion or recursion-like behavior. Was there a question? No. Okay, great. Oh, and the most recent variant was called supernova that achieves like non-uniform incrementally verifiable computation. So this is useful in the context of like state machines, basically. So it's a fun read, I recommend it, but we will not go into it. So with what time I have left, I want to talk about proof composition, which is the composition of heterogeneous proof systems. So now why one might want to do something like that is because some proof systems are better as inner proofs and some are better as outer proofs. What do I mean by that? So, for example, the zkSNARK proof system has a very fast prover, but at the expense of producing a huge proof. Whereas the Groth16 prover is relatively slow compared to zkSNARK's. But as we know, the Groth16 proof is constant sizes 3 group elements, the smallest known so far. So what if we could implement a zkSNARK verifier in a Groth16 circuit? So we would prove our computation, fast prover, quickly produce this huge proof, and then just dump it into this slow prover. Now it's okay that we're doing something in a slow prover because we're doing the zkSNARK verifier, which is sublinear. So we're doing a smaller thing anyway in the slow prover. And we end up with a constant size proof that we can then put on Ethereum, for example. Usually that's why people do it. They want to send us as small a proof as possible to save money, to verify it cheaply. So this is being done by, for example, it's being done by a bunch of zk EVM projects. So these projects, they stuff the whole Ethereum virtual machine state transition into a circuit. And it's a huge circuit, as you might imagine. And yet, at the end of the day, they want to publish that proof on chain. So they had better figure out some way to shrink the proof. Yeah, so that's the most widely used technique. It's just verifier X and prover Y. There are other techniques for proof composition. So for example, commit and prove. There's a very nice paper called zkSNARK that basically allows you to share a witness across two different proofs and then later check that some commitment, that the two commitments provided by these two proofs, in fact, are commitments to the same underlying information. So it's a way to, if you have some computation that is heterogeneous, so for example, let me see. So for example, there's a lot of hash functions in one part, and then there's a bunch of range checks in the other part, and there's like Boolean stuff in the third part. And we know optimized proof systems for each of these separate parts. So why not let each proof system do what it's designed for, and then link all those proofs at the end. So that's what zkSNARK, that's how they do it. Yeah. I'm skipping a lot here. I will put the slides are on the website anyway. Yeah, I think I'm actually done. So the next 2 lectures, I believe, will go into application design. So basically, you're moving into a different headspace. You're thinking about properties of higher level properties of protocols that make use of these primitives. But hopefully, the lectures up till now have given you a solid understanding of the primitives and have given you sort of the confidence to, read new papers about them and to try and understand all the different constructions. Thank you.
There's a question from Zoom if you want to take it.
Yeah.
About 15 minutes ago, and the question was, is it constant time? Doesn't it have to be t0 n, where you can just complicate some of it? This one.
Oh, I know this person.
Yeah, they can hear you, so you can answer.
Where n is the number of because in addition, you need to check the root hashes of all historical blocks to verify that the SNARK corresponds to it. Well, I suppose at each step you would check that the block hash was computed correctly. And then, yeah.
The question was, is it constant time, I guess, something like that.
Yeah. It is constant time because you don't have to go back and do like an ON check of all the block hashes separately. At each step, you check that the block hash was derived correctly from the previous one.
For a lot of it, yeah. I can't
Okay.
consider it. I think
There's no motion. Ah, you're right, that makes sense.
Thank you.